Have you ever really stopped to think about how data gets from, say, your office in one city to another one 1,000 miles away? I mean, it's not like there's one single dedicated wire connecting the two buildings. So, how does it actually work? How does your data navigate that huge, complex web to find its exact destination?
Right. Picture this. Your company has an office in New York and another one in San Francisco. They need to talk to each other constantly and securely. Laying your own private coast-to-coast cable, that would be just astronomically expensive. This is the exact problem that wide area networks, or WANs, were built to solve.
So, in this explainer, we're going to break down one of the key technologies that made all this possible. We'll start with the challenge, look at a really clever solution called Frame Relay, and then we'll demystify the magic behind it all, the virtual circuit. We'll get into how they're set up, how they're addressed, and why this whole concept is so incredibly important. Okay, first things first, let's set the stage. To really get the solution, you have to appreciate the scale of the problem. And that means understanding the difference between talking to someone in the same room versus talking to someone across the entire country. On one hand, you've got your local area network, your LAN. This is what connects the computers in your office or your house. It's super fast, it's cheap because the distances are tiny. But connecting between cities or even countries, that needs a wide area network, a WAN. And these are just naturally slower and way more expensive to build. So the real challenge has always been, how do we make them as efficient as possible? So, how do you do that? Well, one of the most important answers to that question was a technology called Frame Relay. And honestly, it was a total game changer for building efficient and affordable WANs. Frame Relay is basically a super efficient postal service for your data. It's a standardized way to package and switch data through a provider's network. And the clever part is it doesn't get bogged down with a ton of error checking. It kind of assumes the network underneath is pretty reliable, which makes it fast, really fast, perfect for connecting different LANs. And this diagram shows you the basic idea. Your device, let's say it's your router, sends data frames into the service provider's network. From there, your data hits this cloud and gets zapped from switch to switch until it pops out at its destination. But how does the cloud know exactly which path your data is supposed to take? And that question brings us to the absolute core of our topic today, the virtual circuit. This is the secret sauce. This is what makes technologies like Frame Relay so incredibly powerful. It's the invisible highway your data travels on. So, a virtual circuit is a predefined path that cuts through the shared network. Now, to your devices on either end, it looks and feels just like a direct, private wire connecting them. But in reality, it's a logical pathway that's hopping across all of the provider's shared equipment. This is the key. Let me say it again. It's a logical path, not a physical wire. This isn't some dedicated cable that's just for you. It's more like a digital agreement between the network switches on how to forward your data. And this is what allows a provider to take one massive, expensive network and logically slice it up for hundreds of different customers. That's what makes it affordable for everybody. This visualizes it perfectly. See that dotted line? Data from host 1 needs to get all the way over to host 5. The virtual circuit defines that the path will always go from switch A to E to C and then to D. Every single packet follows that exact same logical route. It's what ensures your data arrives in the right order, even though it's sharing the physical wires with a whole bunch of other traffic. Okay, so we've got these logical paths, but are they always on, or are they just created when we need them? Well, it turns out you can have it both ways. Let's take a look at the two main types of virtual circuits. First up, you have permanent virtual circuits, or PVCs. These are the most common. A network admin sets it up once and boom, it's always on, always ready to go. Think of it like a leased line. It's super reliable, but you're paying for it whether you're using it or not. Then, on the other hand, you have switched virtual circuits, or SVCs. These are temporary. They're created on demand, which makes them way more cost-effective for connections you only need once in a while. And the life cycle of that SVC? It's really just like making a phone call. First, you have the call set up to establish the connection. Then you transfer your data. If there's a pause, it goes idle. And when you're all done, the call is terminated. And that circuit is torn down, freeing up all those network resources for someone else. So if these are all just logical paths floating around in this giant shared cloud, how does a switch know which data belongs to which virtual circuit? It needs an address, right? A little label that says, hey, this packet belongs on the highway to San Francisco.
And that label is called the Data Link Connection Identifier, or DLCI for short. It's really just a simple number that gets stamped onto every frame of data. When a switch sees a frame come in, it just looks at the DLCI number. That number tells it exactly which virtual circuit it belongs to and where to send it next. Simple as that.
Here is the absolute best way to think about it. Your physical wire into the network. That's like the main phone number for a huge office building. The DLCI is the extension. It's what directs the call, or in our case, the data frame, to the one specific desk, the one correct destination, inside that whole building. And these DLCIs are just numbers. And while there are technically more available, service providers usually assign values in this specific range, from 16 up to 1,007 for all their customers. The other numbers, they're usually reserved for management and other special network tasks. Now, this is a really key technical point that can trip people up. The DLC value is only meaningful on one specific link, the one between your router and the provider's first switch. This means your New York to San Francisco circuit might be labeled DLC 100 in New York, but on the San Francisco side, that very same circuit could be identified by a totally different number, maybe DLC 250. It's locally significant, not a globally unique address.
All right, let's zoom out and put this all together. Why was this whole idea of creating virtual connections over a physical network so important? I mean, what did it really give us?
The benefits were huge. First off, by creating these logical paths, providers could share their expensive infrastructure, which just slashed costs for everyone. It lets them efficiently slice up your bandwidth for tons of different users. And because it allows for bursty traffic, short periods of high activity then nothing, it's perfectly suited for the way local networks actually communicate with each other.
And this core concept, creating virtual logical layers on top of physical hardware, it didn't stop with Frame Relay. It is everywhere in technology today. We're talking virtual machines, virtual private networks, VPNs, software-defined networking, the list goes on. So, as a final thought, think about it. From the browser tab you're in, to your operating system, to the network connection itself, how many virtual layers are you interacting with right now just to watch this? The answer is a lot.